Okay, this video is going to show you how to calculate pH, pOH, hydrogen ion concentration, or hydroxide ion concentration if you are starting with a base. So that's what C and D are. So I'm going to start with C first. Like the acids that we did, potassium hydroxide is a strong base. So that means when it is added to water, it is going to dissociate into 100% ions. So whatever the concentration of the base itself is, if that's a 1-to-1 ratio, molar ratio, then the concentration of the base will also be the concentration of hydroxide ion. So what I can do here is I'm going to say, because I've got pOH, or I'm sorry, because I've got hydroxide ion concentration, so I want to write that first. Hydroxide ion concentration is 9.7 times 10 to the negative 9th molar. I am going to start with pOH. So I will do negative log of 9.7 times 10 to the negative 9th. And when I do that, I get 8.01. Okay, checking significant figures. In the prompt, my molarity had two sig figs. So what I do for pH or pOH is that means I'm going to use two numbers after the decimal. So my pOH is 18.01. So to get pH, I'm basically doing 14 minus pOH, which is 8.01. So that will give us 5.99. And this is not just 14, it's actually 14.00, so I'm going to maintain the same number of significant figures. So my pH is 5.99, which means this solution is acidic. Now this is kind of like that last problem that we did, which would be like B, because if I think about the concentration of this base is so small, and really what I need to look at to tell me this is I am looking at the exponent. If it is smaller than 10 to the negative 7th, then I need to think about how water contributes more to the pH of the solution than either of these super dilute acids or bases. So if I consider water, then I know that I have, let me write this again just on the off chance that you didn't view the entire first video. I've got water that is auto-ionizing to make hydronium and hydroxide ions. This is a pure liquid. So if I'm writing the kW for water, it will be concentration of our products times the concentration of the products multiplied together divided by the concentration of the reactants. But these are both pure liquids, so they're not included. So our kW is 1 times 10 to the negative 14th. So both of these are X because I don't know what they are. And I could set up an ice chart if you don't understand that. I can show you how to do that at tutoring. So basically this is X squared. So X is equal to 1 times 10 to the negative 7th. That is molarity. That is for both hydronium ion and hydroxide ion. So if I were to do negative log of, let's do H plus, 1 times 10 to the negative 7th to get pH. Then I would get 7.00, which would be neutral. And because this concentration right here, this hydronium ion concentration is larger than this, water contributes more to the pH of the solution than this super dilute base does. Okay, next example. So we're doing D. So let me go erase this. And I'm going to do D. So what I want to do here is I want to think about, this is a strong base, so it is going to completely dissociate or split into its ions. But because I have a subscript of 2 for my hydroxide, I need a coefficient of 2 in front of this hydroxide. Okay, so thinking back to what we did last semester, if my calcium hydroxide were 1 molar, that would mean my calcium ion was 1 molar and my hydroxide ion was 2 molar. Likewise, if calcium ion was 0.5 molar, calcium hydroxide were 0.5 molar, then our calcium ion would be 0.5 molar because it's the same molar ratio, and then hydroxide would be twice as much, would be 1 molar. So now I want to take this and I want to do it with a scary number. So I'm going to take 1 times 10 to the negative 3rd because I have a subscript of 2. To get the hydroxide ion concentration, I need to do 2 times 1 times 10 to the negative 3rd. And when I do that, we are going to get 2.0 times 10 to the negative 3rd molar for our hydroxide ion concentration. If you're not sure what I'm talking about there, think about if that were to be dissolved in the solution, for every 1 mole of calcium ion, we would have 2 moles or twice as many moles of hydroxide ions, which is why we need to double it right there. Okay, so let's continue. We've got hydroxide ion concentration. Let's get hydrogen ion concentration. And I'm going to do this using, ion product of water. So 1 times 10 to the negative 14th equals hydronium ion concentration, which I don't know what that is, times 2.0 times 10 to the negative 3rd. So I am going to divide both sides by 2.0 times 10 to the negative 3rd. And when I do that, I get 5, whoops, I lost my marker, sorry. I got, there we go, 5.0 times 10 to the negative 12th molar. So that tells us hydronium ion concentration or hydroxide ion concentration. Okay, now I want to calculate pOH. So I can calculate pH first, or I can use my hydroxide ion concentration, which is what I'm going to do. So I'm going to say that pOH equals the negative log of 2.0 times 10 to the negative 3rd. So when I do that, I get 2.70. And then what I want to do is calculate, what color do I want to do? I want to calculate pH. So I'm going to do 14 minus 2.70, which will give us 11.30, which would tell us that that solution is basic. And if I look at it, that would make sense because I've got a base And this molarity is greater than the hydroxide ion concentration would be in water. So that makes complete sense.